Today our topic is open sets in R. In this lecture we define open sets in R and give examples, and also we prove some properties of open sets in real number. To define open sets, we have to first define interior point of a set, and we try to give this definition geometrically. Now we know a real number is a point on a line which is called real line, and each point on this line is also a real number. That is, there is a 1-1 correspondence between the set of all points in a line and the set of all real number. So to draw a point or to draw a real number, we first draw a line, and to show a real number we take a point on this line. Suppose A be a real number. The delta neighborhood of A means the open interval A minus delta to A plus delta, having center A and distance of these 2 points is delta, and delta neighborhood of A is denoted by this symbol n delta A, which is the open interval A minus delta to A plus delta, that is, which is the set consisting of all real number which lies in between A minus delta and A plus delta. We now define interior point. Interior point of a set. Let S subset of R, S subset of R, S be a subset of R. A point C belongs to S is called an interior point of S if there exists delta greater than 0 such that n delta C subset of S. Now we show it geometrically. Suppose C be a point on the line. If there exists a neighborhood, that is, there exists delta such that all the points in this neighborhood is also a point of S, then we say C is an interior point of S. C is an interior point of S. We now give an example. Suppose we consider open interval 1, 2. Suppose S is equal to open interval 1, 2. 1, 2. Suppose this is 1, this is 2. And C be a point in open interval 1, 2. Suppose C belongs to open interval 1, 2. So 1 less than C less than 2. 1 less than C less than 2. This implies C minus 1 greater than 0, 2 minus C greater than 0. This part, this distance as well as this distance is always greater than 0. Suppose delta সমান mean C minus 1, 2 minus C. This is two positive number and we take minimum of this is delta. in this in this figure, this part is delta, and if we take a neighborhood having center C, radius delta, then this neighborhood is a subset of open interval 1, 2. We now prove mathematically. Actually, we want to show that C minus delta, C plus delta subset of open interval 1, 2. If we can show this, then C will be a limit point of open interval 1, 2. That's it. In this figure, we can see easily that this open interval is a subset of this, but we prove it mathematically. Suppose let x belongs to this. To prove this is a subset of this, we take any point x belongs to open interval C minus delta to C plus delta. We have to show that x belongs to open interval 1, 2. Then C minus delta less than x less than C plus delta. Since delta is equal to mean of C minus 1 to C minus 1 2 minus C, so delta less than equal to C minus 1 and delta less than equal to 2 minus C. So 1 less than equal to C minus delta and C plus delta less than equal to 2. Now C minus delta less than x, the 1 less than equal to C minus delta less than x and x less than C plus delta, x less than C plus delta less than equal to 2. That is 1 less than x less than 2 implies x belongs to open interval 1, 2. So each point of this subset belongs to each in this set 1, 2. So n delta C subset of 1, 2. So each point of S is an interior point of open interval, interior point of S. Now, using the definition of interior point, we now define open sets in R. Open set. Let S subset of R. S is said to be an open set if each point of S is an interior point of S. If each point of S is an interior point of S, then S is an open set. S is an open set. Now, we give example. Open interval 1, 2 is an open set. We have proved, we have taken any point in this open interval 1, 2 and we show that this is an interior point of open interval 1, 2. Since C was an arbitrary point of open interval 1, 2, so each point of open interval 1, 2 is an interior point. That's why this is an open set. Secondly, actually open interval AV, any open interval is an open set. Now third example is R is an open set. R is an open set. Why? Since R is the whole real line, if we take any point and take any neighborhood center that point, then this neighborhood is always a subset of R, because we consider each point from the set of real numbers. So every neighborhood of every point is a subset of R. So each point of R is an interior point. So R is an open set. 4 number, phi is an open set. Since the empty set has no point, so we can consider each point of this set is an interior point. Since this contains no point, so this is an open set. So these are examples of open set. Now we give an example which is not an open set. Not an open set. Singleton set A is not an open set. Not an open set. If we take any point, suppose this is A, and any neighborhood centered at this point, then this neighborhood contains infinite number of points. Infinite number of points which are different from A. So this neighborhood cannot be a subset of this set. So any singleton set is not an open set. Not an open set. Next, closed interval AB is not an open set. Not an open set. Since if we take closed interval AB, A to B, closed interval AB, then A is not an interior point, because if we take any neighborhood centered at A, then the left hand part contains points which are not the point in this, which are not belongs to this closed interval AB. So the left end point A is not a limit, not an interior point. Similarly, the right end point B is not an interior point of this set. So this is not an open set. Not an open set. Now we prove some important result, and using this result we can get more open sets. First, we prove that union of two open sets in R is an open set. Is an open set. Take suppose G1 and G2 be two open sets in R, and G shaman G1 union G2. We now show that G is an open set. That is, we have to show that each point of G is an interior point of G. Take any point, let C belongs to G. C belongs to G. Then C belongs to G1 or C belongs to G2. Either C belongs to G1 or C belongs to G2, or maybe C belongs to both of them. Without loss of generality, without loss of generality, suppose C belongs to G1. Now we have taken G1 is an open set and C belongs to G1. So C is an interior point of G1. Since G1 is an open set, C is an interior point of G1. So there exists delta greater than 0 such that n delta C subset of G1, this is subset of G1 union G2, and this is equal to G, implies n delta C subset of G. So we take any point C from this set G and we get a neighborhood of C which lies wholly in G. So C is an interior point of G. So C is an interior point of G. Hence G is an open set. G is an open set. And since G is open set, so we can say union of two open sets is an open set. And in this similar way, we can prove that union of finite number of open sets is an open set. Union of finite number of open sets in R is an open set. Actually, we know open interval is an open set. So open interval 1, 2 is an open set, and open interval 3, 4 is also an open set. Open interval. So their union, that is 1, 2, open interval 1 to union open interval 3, 4 is also an open set. This is an open set. Using this theorem, we can say that this is an open set. Also, this is an open set. 1 to infinity, unbounded open interval. A to infinity, this is an open set. And minus infinity to A, this is also an open set. Open set may be bounded or may be unbounded. Now, in this similar way, we can prove that union of arbitrary collection of open sets is an open set. Any collection, if we take any number of open sets, then their union is always an open set. Now, if we take intersection of two open sets, which is open or not, our next theorem is intersection of two open sets in R is an open set in R. Now we prove this result in details. Let G1 and G2 be two open sets in R and G समान G1 intersection G2. We now show that G is an open set. If G is equal to 5, then G is an open set, We know empty set is an open set. Suppose G not equal to 5 and C belongs to G. C belongs to G. Then C belongs to G1 intersection G2. This implies C belongs to G1 as well as C belongs to G2. Here C is a point and C belongs to G1 and C belongs to G2. Now G1 and G2 are two open sets. So C is an interior point of G1 as well as C is also an interior point of G2. Since G1 and G2 are open sets, there exists delta 1, delta 2 greater than 0 such that n delta 1 C subset of G1 and n delta 2 C subset of G2. Suppose this is a delta 1 neighborhood, C minus delta 1 to C plus delta 1, and suppose this is delta 2 neighborhood. One of them must be lies wholly in the other neighborhood. Since these are two positive real number, delta 1 and delta 2. If we take delta समान mean of delta 1 delta 2, let delta समान mean delta 1 delta 2, then delta greater than 0, and which is minimum. Suppose delta 1 is minimum, then n delta 1 C wholly lies in n delta 2 C. Then we can write n delta C subset of n delta 1 C subset of G1 and n delta C subset of n delta 2 C subset of G2. So n delta 2 is a subset of G1 as well as G2. So n delta C subset of G1 intersection G2, which is equal to G. So C is an interior point of G. We have taken any point C from the set G, and we now show that C is an interior point of G. So each point of G is an interior point of G. So G is an open set, that is intersection of two open sets in R is also an open set. And if we take finite number of open sets G1, G2, Gn, then their intersection is also an open set, that is intersection of finite number of open sets is an open set. All are open sets in R, then open set in R. If we take proof is similar, if we take G1, G2, Gn, n open sets, and take G equal to intersection of these open sets. If G equal to 5, then clearly G is an open set. If G not equal to 5, take any point C from G, then C belongs to G1, G2, and C belongs to Gn also. And since these are all open sets, so we get delta 1, delta 2, delta n, such that n delta 1 C subset of G1, n delta 2 C subset of G2, and n delta n C subset of Gn. And if we take delta समान mean of delta 1, delta 2, delta n, then delta is also greater than 0, and n delta C subset of Gi for all I equal to 1 to n, so n delta C subset of G. So in this case C is also an open set of G. Since C is an interior point of G, and hence G is an open set, that is intersection of finite number of open set is also an open set. Now intersection of arbitrary collection of open set is open or not. Here the result is not hold, that is intersection of intersection of arbitrary collection of open sets may not be open,